Good morning, friends. Now, in chapter number 10, light reflection and refraction. In this chapter, we'll start the topic the refractive index. So, first, what is the meaning of refractive index of a medium? So, for that, a ray of light that travels obliquely from one transparent medium to another transparent medium will change its direction in the second medium. The extent of the change in direction that takes place in a given pair of media is expressed in terms of refractive index. The constant appearing in the equation sin I upon sin R is equal to constant. Now, suppose that this type of question will ask explain the term refractive index or explain the relative refractive index. So for that we'll start from the speed of light in vacuum is a fundamental constant of nature. It is denoted by small c. For all ordinary purpose, the speed of light in vacuum, as we know that c is equal to 3 into 10 raised to 8 meter per second. In the air, the speed of light is only marginally less compared to that in vacuum. Therefore, the speed of light in air is taken as 3 into 10 raised to 8 meter per second. The refractive index can be linked to an important physical quantity, the relative speed of propagation of light in different media. And it turns out that light propagates with different speeds in different media. Consider a ray of light traveling from medium 1 into medium 2 as shown in the figure. So here let V1 be its speed in medium 1 and V2 its speed in medium 2. The refractive index of medium 2 with respect to medium 1 is given by the ratio of the speed of light in medium 1 to the speed of light in medium 2, denoted by eta 21. Here eta is known as the refractive index. So eta 21 is equal to speed of light in medium 1 upon speed of light in medium 2, that is V1 upon V2. Let it equation number first. By the same argument, the refractive index of medium 1 with respect to medium 2 is represented as eta 12 and it is given by eta 12 is equal to speed of light in medium 2 divided by speed of light in medium 1 is equal to V2 upon V1. Let equation number 2. Now, for that, the question explain the term absolute refractive index. So in absolute refractive index, the refractive index of medium with respect to the vacuum is called the absolute refractive index of the medium. Again I repeat, the refractive index of medium with respect to the vacuum is called the absolute refractive index. It is the ratio of the speed of light in vacuum c to the speed of light in the medium v and denoted by eta m. Again, it is the ratio of the speed of light in vacuum c to the speed of light in vacuum v and denoted by eta m. So eta m is equal to speed of light in air or vacuum divided by speed of light in medium. So this is equal to speed of light in air, that is c, and speed of light in medium, that is v. So c by v. Let equation number 3. The absolute refractive index of medium is simply called its refractive index. Again I repeat, the absolute refractive index of medium is simply called its refractive index. For example, the speed of light in glass is 2 multiplied by 10 raised to 8 meter per second. For example, the speed of light in glass is 2 multiplied by 10 raised to 8 meter per second. Absolute refractive index of glass, that is eta g, is equal to 3 multiplied by 10 raised to 8 divided by 2 multiplied by 10 raised to 8, and this approximately, that is 1.5 value will be given, and the absolute refractive index of any medium is greater than 1. So here the absolute refractive index of some material medium, that will be given, as we know that the material medium, that is air medium, and the refractive index of air, that is 1.0003. That is ice material, that is refractive index of ice, that is 1.31, water 1.33, alcohol 1.36, kerosene 1.44, fused quartz 1.46, turpentine oil 1.47, benzene 1.50, crown glass 1.52, that is Canada balsam, that is, it is one type of the yellowish resin used in microscope slides. A refractive index is 1.53, rock salt 1.54, carbon disulfide refractive index is 1.63, dense flint glass 1.65, ruby 1.71, sapphire 1.77, and diamond, that is 2.42. So from this table, an optically denser medium may not possess greater mass density. Okay, from this table we observe that an optically denser medium may not possess greater mass density. For example, kerosene, having high refractive index, is optically denser than water, although its mass density is less than that of water. Here the refractive index of water is 1.33, we have to be observed in this table. So what does it mean? Here the refractive index of water, that is 1.33. This means that the ratio of the speed of light in vacuum to the speed of light in water is equal to 1.33. Again I repeat, the refractive index of water, it is 1.33. This means that the ratio of the speed of light in vacuum to the speed of light in water is equal to 1.33. Now the again question like that, what is the optical density of medium? What is the optical density of the medium? So for that, the ability of the medium to refract light is expressed in terms of its optical density, and optical density has a definite connotation, and it is not that same as mass density. Here again, that is one type of question will be arises, that what do you mean that the optically denser medium and optically rarer medium? So in comparing two media, the one with the higher refractive index is said to be optically denser than the other. The other medium of lower refractive index is said to be optically rarer than the first one. The speed of light is higher than optically rarer medium than in an optically denser medium, and ray of light traveling obliquely from one optically rarer medium to another optically denser medium slows down and bends towards the normal at the point of incidence, while when it travels from an optically denser medium to an optically rarer medium, it speeds up and bends away from the normal to the point of incidence.